So I'm just going to download this here. Let's go ahead and open this up. Editing. So what I'd like to do with these, we have the A, B plus C, D type reaction here. So A is our calcium ion. Stupid pen. B is carbonate. And then sulfuric acid, A is going to be the hydrogen of the sulfuric acid. This is H2SO4. And B is going to be the sulfate. And so we have calcium sulfate and hydrogen carbonate. Hydrogen carbonate, we don't call hydrogen carbonate. What do we call that instead? So everybody got the products to this, or people are getting stuck with the products? You think you got it? All right. Let's take a look. Oops. So let's see if this is a little easier to follow. Calcium carbonate and sulfuric acid. Sulfuric acid is H2SO4 and it's aqueous. If there's water present, then carbonates, phosphates, and chromates are all insoluble except for group 1 and ammonium. So this is an insoluble solid. So I write solid here to indicate that it's insoluble. But H2SO4 is soluble, that's aqueous. But I usually omit aqueous. So I don't write aqueous, it's just because it takes time. And instead, what I'm going to do is, if it's blank, that means it's aqueous. Aqueous is the most common state we encounter. What that means is, if it's not aqueous, I have to write solid, liquid, or gas. And so I'll make sure to write solid here. And so what we're going to do is we're going to take, when I do double replacement reactions, I'd like to just switch the anion. So this had the carbonate ion, this has the sulfate ion. So I'm going to pair calcium with sulfate, and so I form calcium sulfate, and then hydrogen with carbonate. Hydrogen is a +1, carbonate is a -2. So I'm going to need 2 hydrogens for every carbonate so that the charge is balanced. But the first thing you should recognize immediately is H2CO3. What's the name of H2CO3? Carbonic acid. Okay, the next thing you should realize immediately is that carbonic acid is not stable. Carbonic acid immediately decomposes into H2O liquid and CO2 gas. So often what we're going to see is we're not going to see carbonic acid. If we see carbonic acid, they'll put it in quotation marks to indicate that it's not stable. It's going to decompose. And so let's see, do we see carbonic acid on this chart up here? Yes, I do. Look on the right column, 4th acid down. Do you see carbonic acid? Right column, 4th acid down. But what's in the parentheses there? CO2 and H2O. That's because carbonic acid is unstable, right? And what's stable is H2O and CO2. There's no problem with that. And so ideally, we replace the carbonic acid. You shouldn't leave the carbonic acid in the equation, because it's not what's going to form in this particular reaction. What's going to form are bubbles of CO2 gas. That's what's going to form. This is why geologists carry, they don't carry sulfuric acid, they carry hydrochloric acid, but any acid will do, because acid is going to supply the H+, and H+ with carbonate makes carbonic acid. And we're going to get the bubbling here. Well, if we get bubbles of gas forming, then we know the driving force. What is the driving force? Gas formation. But this particular reaction has multiple driving forces, as I said H2SO4. One driving force is gas formation.
Can you go over driving force again? What is that? I'm confused.
Okay. If there's no driving force, then there's nothing to push the reaction forward. And so we need a driving force for the reaction to occur. If there's no driving force, then nothing's going to happen, and we face no reaction. And so all we need is one. I gave you three potential driving forces. What were the three potential driving forces? Gas formation. So this reaction should occur. We're forming gas. CO2 is a gas. And so we have driving force here, therefore we expect reaction to take place. What are the other driving forces?
Weaker acids?
Yeah, weaker acids. Going from a stronger acid, it doesn't have to be a strong acid, just a stronger acid to a weaker acid. Okay, H2SO4 is a strong acid. Is carbonic acid a strong acid? No, that's a weak acid. So in this case, we're going from a stronger acid, SA, to a weaker acid, WA. And so that's what I'm going to use. S does not stand for strong. It doesn't have to be strong. It just has to be stronger than the other. We can look at the acid chart. That's an acid chart up there on the wall for the ranking. The only thing is, you have to be aware of something called the leveling effect. What is the leveling effect? If you don't know, you probably haven't seen that in the book. It's not in the book, but you can look it up online. There's lots of resources for the leveling effect. But can somebody summarize the leveling effect briefly? No, that's not it.
It's the top 7 strongest acids, and when the reaction happens between them, double replacement doesn't occur because in theory they're the same strength, so it wouldn't create a reaction.
Yeah. Basically, the leveling effect means that when you rank the top 7 acids there, you can rank them, but in water, they're all the same strength. And so those 7 acids are equal in terms of strength, therefore those aren't going to determine if we're going to get a reaction. So let's say we have H2SO4 on the left and we have HCl on the right. Well, the leveling effect is going to tell us it's a tie, basically. But in this case, we have H2SO4 on the left, and what's the acid we have on the right? H2CO3. H2CO3 is a weak acid, and it's definitely a pretty weak acid. Therefore, this is a driving force. But H2CO3, remember, decomposes right away to form H2 on CO2. So does the acid disappear? No, the acid doesn't disappear. And so we could label the weaker acid H2CO3, or we could label the weaker acid H2O or CO2? CO2. CO2 is what we call a Lewis acid. Lewis acids are a little bit more difficult to recognize, but the CO2 would be a weaker acid. You know, what would you rather have in your face? Someone exhaling CO2 or somebody throwing sulfuric acid into your face? Well, CO2 is weak, right? And people, sulfuric acid causes severe burns. And unfortunately, people do that. You've seen people disfigured from getting H2SO4 thrown into their face. But the CO2 would have been a much better acid, for sure, in terms of damage to tissue. Okay. So anyway, that's the driving force. The driving force, why? Because H2SO4 is very reactive. Something that's very reactive is unstable energetically. And so we're going from something that's unstable, high energy, to something that's more stable, low energy. Nature tends to go from higher energy to lower energy, and not the opposite. So that's 2 driving forces. This is pretty good. What's the third driving force? Precipitation. Now, we have to look at sulfates. you know, calcium is not a group 1 or ammonium. So first we look at the cation. It's a group 2. Therefore, we're going to look at the anion. Sulfates are all soluble or insoluble? Sulfates are all soluble. Except for silver, lead, mercury, calcium, strontium, and barium. So calcium is one of the exceptions, and therefore we would think it's a precipitate. And it would be a precipitate here. And so what we do is we'll put a solid here. Oh, shoot. Try that again. It's solid there. So is that our third driving force? We have two driving forces. One, gas formation. Two, the second driving force was stronger acid to weaker acid. And three, precipitation of calcium sulfate. Is this a driving force? Well, in a normal precipitation reaction, you're taking two solutions and forming a precipitate, like in Chem 4, Chem 1A. But in this particular precipitation, we're losing one precipitate or one solvent. It's calcium carbonate. And we're forming another. And so we can't call this a precipitation. What this is a solid to solid transformation, solid to solid. And which direction it goes in the direction of the more stable, lower energy solid. So which one is more stable? Calcium carbonate or calcium sulfate? Well, there's different ways we can tell about stability. One way we can tell about stability is melting point. The higher the melting point, the harder it is to break apart, which means the more stable it must be. That's one. Or, more directly, solubility. The less soluble it is, the more stable. The harder it is to break apart to get into solution. So the less soluble one should be the more stable one. So which one's less soluble, calcium carbonate or calcium sulfate? Well, we can use theoretical approach, but we're not. We're going to use an empirical approach, an observational approach. Did I already look these up? Did we already look these up? Which one was less soluble? What happened to all my writing? Let's see. Did I lose it? I just hit the wrong button, unfortunately. All right, it's going to take me a little bit to get used to this. I just write it on the board. But calcium carbonate, solid versus calcium sulfate. This was less soluble. This one was more soluble. Calcium sulfate, we can dissolve more of that in water, and therefore, which one's more stable, would you say? Calcium carbonate's more stable. So we don't want to say precipitation of calcium sulfate's a driving force because we're sacrificing calcium carbonate, which is not favorable. Calcium carbonate's more stable, right? But regardless, all we need is one driving force. So even if this is happening, that one driving force can drive this reaction forward. And now we have two driving forces, so we expect this reaction to occur. Does that make sense? All right, so if the reaction occurs, then we write out what's called the complete equation of the CE, which for me is going to be the calcium carbonate plus H2SO4 is going to yield calcium sulfate solid plus H2O liquid plus CO2 gas. We had our driving force gas formation and going from a stronger acid H2SO4 to weaker acid CO2. Then we come up with our IE, which stands for the ionic equation. In the ionic equation, we only ionize, we only break apart the strong electrolytes. Can you remind me what the strong electrolytes are?
Strong acids and bases.
Yeah. The strong electrolytes are shown in the center here because these fully light up the light bulb here. The strong electrolytes are the strong acids, strong bases, and the soluble salts. Then we have the weak electrolytes. The weak electrolytes weakly ionize or weakly dissociate. Those are going to be the weak acids and weak bases and insoluble salts are tricky, but we'll just say some heavy metal salts is usually what I do. And so some heavy metal salts are actually weak electrolytes here. Insoluble salts often are termed strong electrolytes with very low solubility. So when we have an insoluble salt, a little bit dissolves, that little bit does break up into ions, but we have such a low concentration of ions that the conductivity is very small. Electrical conductivity depends on three things: number of charge carriers, charge on the charge carriers, and mobility on those things. Okay, the only thing we break apart are the strong. So is calcium carbonate a strong electrolyte? No. If it's not strong, leave it alone. Sulfuric acid, is that strong? Yes, but when sulfuric acid breaks apart, do both protons simultaneously come off? No, one proton comes off at a time. So if we do this in sequence, the first proton comes off. And I'm left with HSO4 minus, which is bisulfate or hydrogen sulfate ion. Does the second proton come off easily off bisulfate? Is bisulfate a strong acid, strong electrolyte? No, it's a weak acid. And therefore, it only weakly ionizes. If it weakly ionizes, we just leave it alone. And so what I'd like you to do here, and this is hard for a lot of people because they learn it differently in Chem 1A and Chem 4. A lot of instructors prefer to break both off. I don't. I'd like you just to break the first one off and leave the second one on.
It isn't doing that, treating it like it's a weak acid.
It is. It is a weak. HSO4 minus is a weak.
Sulfuric acid as a weak acid.
No, we already broke up. No, sulfuric acid already lost its proton. And so sulfuric acid itself is a strong acid. So if we look at sulfuric acid, like say the structure here, this completely dissociates. And so the first proton comes off easily. Okay, once we lose that first proton, then it's no longer sulfuric acid.
Okay.
And so this is why. If both protons could break off at the same time, then that's a different story. Now, the protons aren't breaking off. The protons are being plucked off by water. And so I use H plus and hydronium interchangeably here. But let me do this. Okay, to illustrate the difference between bisulfate and sulfuric acid. Let me ask you this question here. This is going to be bisulfate. It has a negative charge on that oxygen there, negative formal charge, versus sulfuric acid. If you were water, which hydrogen would be more attractive to pluck off? Would it be this hydrogen, or would it be this hydrogen here? If you were water, which one would be a stronger acid hydrogen to pluck off? Sulfuric acid. Well, isn't this sulfuric acid too? No, because this is actually bisulfate, and structurally it's quite a bit different. And so we're only going to pluck off the first one here. Calcium sulfate, is that strong acid, strong base, or soluble salt? No, it's an insoluble salt, so don't touch it. The only things we're going to touch are the strong. Water? No. CO2? No. So leave everything else alone. There are no spectators here, and so the ionic equation and the net ionic equation are the same thing. And so this is kind of what we do for this.
For the ionic equation, we only separate it if it's strong.
Leave everything else alone. You can work on this one. This is another double replacement. This is another double replacement here. This double replacement, let me talk about this one. Here. Lead 2 iodide. Excuse me, what's the formula for lead 2 iodide?
PBI2.
PBI2. And hydrochloric acid? HCl, good. Hydrochloric acid, that's not hydrogen chloride gas, that's hydrochloric acid. Hydrochloric acid consists of hydrogen chloride gas dissolved in water, so this is aqueous. If there's water around, will PBI2 dissolve? Chlorides, bromides, and iodides are all soluble, except for
lead 2.
Yeah. And so this is an insoluble solid, so we'll write solid here. So now we're going to take lead ions and pair them with chloride. So if I take my lead and pair it with chloride, I'll form PbCl2. And I'll take my hydrogen ions and pair it with iodides. And it's going to form HI. It's not balanced. I'll balance it if there's a driving force. Now, is there a driving force here? So take a look at that chart over there. Those are the acids. So let's say we're going from HCl on the left, hydrochloric acid, to HI on the right. HI is called what?
Iodinic acid.
Not iodide acid, but not hydrogen iodide. We call it hydrogen iodide, as the pure substance, but in the acid form, we'd call it hydroiodic acid. Hydroiodic acid, so we're going from hydrochloric acid to hydroiodic acid. Is that a driving force? No, it appears that hydroiodic acid is actually stronger or weaker than hydrochloric acid?
Stronger.
Yeah, hydroiodic acid is stronger. And so, if hydrochloric acid is weaker, it's still a strong acid, and we're going to a stronger acid, hydroiodic acid, then we're going uphill. We want to go downhill. The downhill direction is backwards. Do you see that? We're going uphill. I don't like to climb uphill. I'd like to go downhill when riding a bicycle. It's much easier. You don't run into that resistance. So we're going uphill. However, this is a trick. This is a trick because do you know what the leveling effect is? The leveling effect tells me that I'm wrong. In reality, this is not going uphill. It's not going downhill. It's
Just going side to side.
there's no hill here. That's because the leveling effect tells me that these two acids are the same strength in water. Same strength in water.
The hydrochloric and the hydroiodic acid. So
Yeah. This is called the leveling effect. So let me say what's happening in water. What's happening in water is something called hydrolysis. So if I take hydrochloric acid and I have water present, I don't know why it's doing this here. Then what's happening is water is acting as a base. Water can act either as an acid or a base. So water comes along, and what it's going to try to do is it's going to pluck the hydrogen off. Let's see what's going on here. All right. Unfortunately, my computer hung up. Can't seem to do anything here. All right. Continuing on with the leveling effect here. So when we have water and hydrochloric acid, versus water and hydroiodic acid. Here. Water is going to have an easier time taking the hydrogen off hydrochloric acid than a weak acid. And it's going to have an even easier time taking the hydrogen off an even more powerful acid, hydroiodic acid. And so the stronger the acid, the easier it should be to remove the proton. Since hydroiodic acid is a stronger acid, water will have no trouble removing that. But the situation is water doesn't have a hard time with either of these. In fact, both of these are plenty easy for water to pluck the proton off. And so water plucks off the proton off HCl to form hydronium here and chloride. And water plucks the proton off hydroiodic acid to form hydronium and iodide. Now the thing about the strong acids easily lose their proton, so water has no problem. So if we start off with 1 molar here, HCl, and we start off with 1 molar HI here, what's going to happen is we're going to end up with 1 molar hydronium. Over here, stoichiometry predicts we're going to end up with 1 molar hydronium. So when we look at these two solutions here, the products of these two, can you tell the difference between these two solutions? So for example, I formed 1 molar hydronium here, and I formed 1 molar hydronium here. There's no way to tell the difference. Both of them are 1 molar. And so this is called the leveling effect. The leveling effect is we form the same amount of hydronium. Now, if we have a weak acid, then we're going to form different amounts of hydronium depending on how weak the acid is. So if I throw in HF here, water is going to have a much harder time plucking the hydrogen off HF. Do you recall why HF is such a weak acid from Chem 1A? HCl, HBr, HI are strong acids, but HF is not.
Because the bond between the hydrogen and the fluorine is so strong that it doesn't want to disassociate.
Yeah, it stretches and stretches, and we form what's called an ion pair. An ion pair is not a bond, but just kind of an intermolecular, or more correctly, interionic force. And so it's hard to break. That's why. But anyway, water is going to have a much harder time because it's going to get in a tug of war. It's going to get in a tug of war with fluorine. Who's going to win? Well, predominantly fluorine's going to win because it's a weak acid. Weak acids weakly ionize or weakly hydrolyze with water. And so if there's a tug of war between water and fluorine's typically going to dominate. Sometimes water will win, but we're going to form a lot less. So if we start off with 1 molar HF and we do the same thing, the amount of hydronium we generate is a lot less than 1 molar over here, because fluorine's going to dominate that tug of war, right? And so for strong acids, all the strong acids are characterized by the fact that water will either, there are different ways we can phrase this, but one way is that in water they will dissociate completely or ionize completely, or water will hydrolyze them completely. Okay, that's it for the strong acids. Now, what about HF? Right, so we use this chart in different ways. So what kind of base do let's say I want to deprotonate HF completely. Water's not strong enough. Water's not strong enough to deprotonate HF, but what is strong enough to deprotonate? In other words, what is strong enough to completely neutralize HF? What base? All right, so this is the other way we use the acid-base chart here. And then the acid-base chart we want to get familiar with because we're going to use this quite a lot. And this is the Bronsted-Lowry acid-base chart. One of the things we want to be able to do is to be able to name these. So the names are written here so you can get accustomed or acquainted with these. You know, but you should be able to name these without this up here as well. But one of the ways we use this is like this. Okay, if we got into tug of war, let's take a look at this acid here. The strongest acid on the chart is perchloric acid. Are there any acids that are stronger than perchloric, or is this the strongest acid in the universe? What do you think? Strongest acid in the universe? No, it's not. There are acids that are stronger. They just aren't very common. They're super acids. Some of them are in our book, discussed in the homework. And then there are super bases. In fact, over at USC, one of the professors there, who passed away not so long ago, won the Nobel Prize in Chemistry for his work on superacids and superbases. Professor Ola. It's pretty famous. All right, so going here, HClO4. Let's say we got in a tug of war. So ClO4 minus wants to hold on to that proton, H plus. What if we put it in a tug of war with ClO4 minus? So it's going to be ClO4 minus versus ClO4 minus. Is there going to be a clear winner there? No. What we need is we need a base that's stronger. And it turns out because of the leveling effect, the base that's stronger is we need a base like water. H2O is strong enough. So H2O versus ClO4 minus, if we got in a tug of war there, H2O wins, we form hydronium. And so the way we read this is like this. Since I can't do the pen when it's zoomed in, let me zoom out. Let me do the pen. So the way I read this chart is like this. H2O attacks ClO4 minus. So the base attacks the acid. When that happens, what we form are the products. The products of this will be ClO4 minus and H3O plus. Now, the way we want to read this is we want to go from a stronger acid, HClO4, to a weaker acid. The weaker acid in this case is hydronium. And so this is what we call driving force here. This would be downhill. The opposite side, it looks like it's going uphill. And so when we look at this, water versus ClO4 minus, it looks as if we're going uphill, but we're not going uphill. That's because the base rankings are inverted. So the strongest bases are at the bottom right, the weakest bases are at the top right. And so if we're going higher, that means we're getting weaker. And so this is actually going downhill here. And so what we're doing here is we're going from the stronger base, water, to the weaker base, perchlorate. So if I asked you what base will completely neutralize HF, what base will react with HF? So let's pick a base. Is fluoride going to be effective at neutralizing HF? No. What we need is we need a base that's stronger or a base that's weaker than fluoride. So if there's a tug of war, fluoride versus fluoride, it's going to be a tie. So should we go weaker, like nitrate, or not? This is not nitrate. What is that called? NO2 minus. Nitrite. Nitrite's weaker. They're both pulling for the H plus. Who's going to win? The stronger one. Fluoride's stronger, it's going to win. So is nitrite going to be an effective base for reacting with HF? No. So what bases does HF react with? HF reacts with all bases stronger than fluoride. And so what would neutralize it? A stronger base, like for example, formate. This is a stronger base. Acetate, bicarbonate, hydrogen sulfide, ammonia, cyanide, carbonate, hydroxide, sulfide. All those bases will react with HF. However, these bases shouldn't. Nitrite, no. Dihydrogen phosphate, no. Sulfate, no. Trichloroacetate, no. Water, no. Nitrate, no. Do you see that? And so this is one way we use this chart. We use this chart quite a lot. And so this brings us back to the chemical properties question. What are the chemical properties of HF? You can look at it one by one. You know, will HF react with this? Will HF react with that? Or you can look at it as a group. If we look at it as a group, HF reacts with any base that's stronger than fluoride. And what are those? Well, there are a lot of them. A lot of them. This is not a comprehensive list. This is abridged. So this brings us to this border. Do you see this border here? This border is very important because none of the bases up here can exist in water. Or not bases, these are acids. None of these acids can exist in water. They're all too strong. Water will react with all these acids here. Do you know what the strongest acid that can exist in water is? The strongest acid that can exist in water is hydronium. And therefore, this is the leveling effect, because even if we have a very strong acid like HClO4, well, it doesn't matter because the strongest acid that can exist is hydronium. That's the leveling effect. All those acids are converted to hydronium. And they're all strong acids. Strong acids react or hydrolyze or ionize 100%. Do you know what the strongest base that can exist in water is? This is the other border here. The strongest base. Okay, let's get in a tug of war. We're going to have sulfide versus sulfide. They're both pulling for the hydrogen plus. So sulfide versus sulfide, who's going to win? It's going to be a tie. What we need is a stronger base. What's the stronger base? Amide is a stronger base. So amide will be able to pluck that hydrogen off. But if we try to put these strong bases in water, what's going to happen? Well, water is a stronger acid than all these. I mean, these over here. And so if I take water and sulfide, do you know what it forms? So sulfide attacks water, plucks the proton off. When water loses a proton, it forms hydroxide. If amide plucks a proton off water, it forms hydroxide. Oxide, etc. All these have driving force, because what we're going to do is we're going to do the same thing here. We're going to go from stronger to weaker. And unfortunately, I have to shrink this down. And so let's take amide as an example here. Amide plucks the proton off. In the process, it forms hydroxide. So we're going from amide to hydroxide. Stronger base, SB, to weaker base. And then we form ammonia. And so water is going to go to ammonia. So we're going from a stronger acid, water, to a weaker acid. In fact, ammonia is typically thought of as a base, not an acid. In this case, it reacts as an acid. Some of these are unusual. Ammonia, for example. Ammonia is both an acid and a base. And so it occurs on both sides of the chart. Water is both an acid and a base. So here's water as a base, here's water as an acid. These species are called amphoteric. Water is interesting because it's equal in terms of strength. Ammonia is unequal. It's a much better base than it is an acid. All right, so going back to this reaction here, lead-2 iodide plus hydrochloric acid. Let me write that over here. We see there's no driving force from the acid. All right, what about precipitate? So lead-2 iodide is insoluble in water. Lead-2 chloride is also insoluble in water. So can we say precipitation is a driving force for this? No. That's because this is a solid to solid transformation. And so how do we determine which side is favored? We could look at the solubility. If we look at the solubility, well, I talked about the two-pronged approach in chemistry. The two-pronged approach is, one, the observational approach, the memorization approach, or two, the theoretical approach. And so what we're going to do is we're going to try to apply the theoretical approach to this. And let's try to determine which one of these lattices are going to be stronger. How can you start? Do you guys remember lattice energies? Do you remember ionic bond strength? What makes a good ionic bond? Do you remember Coulomb's law? Okay, what we're going to do is we're going to compare the ionic bonds. Which one do you think has stronger ionic bonds? PbI2 or PbCl2?
PbCl2.
And why is that?
Because the larger the atom gets, the less stable.
Well, maybe not. In terms of reactivity, it is more reactive, but in terms of ionic bonding, it leads to more stability, the smaller it gets. And so if we compare it, let's look at Pb2 plus here. And the difference between iodide versus a Pb2 plus, which is the same size, versus a chloride. So we're looking at a +2 being attracted to -1 here, and a +2 being attracted to -1 here. But the difference is in terms of what we call charge density. So here we have the -1 charge spread out over a bigger volume. Here we have the -1 charge more concentrated in a smaller volume. And so in terms of charge attraction, the PbCl ionic bond should be stronger. This should be weaker. And this is an electrical attraction here. So if you have a concentrated charge versus a more dilute charge, then the concentrated charge will have the greater interaction here. In terms of Coulomb's law, we look at the distance between the center of the charges. So if we look at the center of the lead versus the center of the iodide, there's a longer distance here. And then we treat these charges as point charges. That is, we concentrate the charge in that little point in the center. And over here, the distance is shorter. And the closer they are, the stronger the interaction. And so that's how we look at it in Coulomb's law. In terms of charge density, we look at the concentration of the charge. So if PbCl2 has a stronger ionic bond, then that means it's harder to break apart. If it's harder to break apart, that means it's less soluble and more stable. And so we predict this one to be more stable. But one of the things here is we're treating the bond as being 100%. Remember we talked about this, formal charge versus oxidation state. What's the difference between formal charge and oxidation state? Formal charge, we treat the bond as being 100% covalent. Oxidation state, we treat the bond as being 100% ionic. But the reality is somewhere in between. Here we're treating the bond as 100% ionic, right? We're just looking at it from a pure charge, what we call electrostatic point of view. All right, so we predict this. So there should be a driving force. We're forming a more stable PbCl2. If that's the case, what we do is we continue doing this. We'll balance it. In order to balance it, I need two HCl's. I'm going to form two HIs. Again, I omit the AQ and write in solid, liquid, and gas. They occur. When I do the ionic equation, do I break apart PbI2? No. Do I break apart HCl? Yes. That would break apart into two H pluses and two Cl minuses. Do I break apart PbCl2? No. Do I break apart HI? Yes. That would break apart into two H pluses and two I minuses. And then the H pluses would be spectators. That's kind of a more theoretical approach. We didn't really have stuff totally memorized. We would have to know that, chloride's smaller than iodide. Iodide's a lot bigger, right? It has another shell of electrons. However, whatever theoretical approach we use, it has to agree with observations. It has to agree with experiment. Experimental observations are fact, as long as they're reproducible. That's factual knowledge. And so let's see if our theoretical approach agrees with experiment. So this is what we kind of hypothesize here, that PbCl2 should be less soluble, more stable. All right, so what we're going to do is we're going to take a look at we'll just go to Wikipedia, and we're going to look up PbI2. Wikipedia data for this is pretty decent. You have to be careful because sometimes it isn't so reliable, the Wikipedia entries, but this is pretty reliable usually. And so when we look at the solubility of PbI2 is 0.76 grams per liter. Do you see that here? At 20 degrees C. 0.76 grams per liter. PbI2. Let's go to PbCl2 next. When we look at PbCl2, we see 0.99, about 1 gram per 100 milliliters. So the units are different. PbI2 was 0.76 grams per liter. So about 1 gram in the liter, or 3/4 of a gram in the liter. PbCl2 is 1 gram per 100 milliliters. So I'm going to have to multiply it by 10. And so its solubility is about 10 grams per liter. Does that sound very insoluble to you? No. I mean, that's a lot. 10 grams of lead-2 chloride in a liter, but we still call it insoluble because of the cutoff. There's got to be some cutoff. But it's quite soluble for an insoluble salt. Is that what we predicted? So PbCl2 is about 10 times more soluble in water. That's not what we predicted. Let's go back and look at what we predicted. What we predicted was that the ionic bond strength in PbCl2 should be a lot stronger and therefore harder to break apart. And so what's wrong? is the experimental data wrong, or is my theoretical analysis wrong? Well, when it comes to experimental fact versus theory, you know which one always wins? Experimental fact always wins. So there's a problem with my theory. What could be a potential problem with my theory? One of the big problems with my theory is the assumption I made. I assumed that the bonding is 100% ionic. With heavy metals, it isn't the case. So, for example, when you look at the solubility rules, we had lead 2. What happened to lead 4? Lead 4 chloride is soluble because lead 4 chloride forms molecules. When something forms molecules, what type of bond is that typically? The things that form molecules versus ionic lattices typically form what type of bond? Yeah, like molecules like water. What kind of bond does water have? Is that ionic or is that?
Covalent.
It's covalent. So, molecules will form covalent bonds. And that's what's happening here. What's happening here is heavy metals have a heavier covalent contribution. And so here, what we did was we assumed 100% ionic bonding. And we didn't factor in any kind of covalent interaction in here, but it turns out this is wrong. Solubility shows it otherwise. And so what we're going to do here is we're going to take a look at this. There's a significant covalent contribution to the bonding. This is why in my solubility rules, the weak electrolytes are the weak acids, weak bases, and some heavy metal salts. The heavy metal salts, there's some considerable covalent bonding interaction in there. And so what we're going to have here is this. When we form a covalent bond, what makes a good covalent bond? Well, we can use different theories to analyze our covalent bond. The two most common bonding theories are valence bond theory. In valence bond theory, what makes a covalent bond? You take one atomic orbital, like an sp3, and overlap it with another atomic orbital, like an sp3, and you form an sp3 sigma bond. Or you take a p orbital and a p orbital, and you form a pp pi bond. That's one. But valence bond is not a full quantum mechanical approach. What is the full quantum mechanical approach to bonding called? Molecular orbital theory. So in molecular orbital theory, we do not do overlap of atomic orbitals. Instead, we do LCAO. So can somebody remind me what LCAO stands for in molecular orbital theory? LCAO. So what I'm going to do is I'm going to look at MO theory. And in MO theory, we want LCAO. We don't do an overlap of atomic orbitals. AO stands for atomic orbital. LCAO stands for, what do you do in when you generate MO diagrams, what do you do with the atomic orbitals? So you have an S orbital and an S orbital, and then you generate two new orbitals called molecular orbitals. And what did you do with those S orbitals? You know, one becomes a regular bonding, the other becomes an anti-bonding. Remember that stuff at all? That was the LCAO part. So you take an s orbital over here on atom A, an s orbital on atom B, and then you do an LCAO, and you generate a sigma 1s bonding and a sigma star 1s anti-bonding, and that was called a linear combination of atomic orbitals. So we don't overlap them, we do a linear combination. That linear combination results in a bonding and an anti-bonding, MO. What makes a good linear combination? What makes a good linear combination is getting more into the theory of this, but it has to do with HSAB. HSAB. Tristan, do you remember HSAB? No. HSAB just looks at what types of orbitals form good LCAO. So if you take a big polarizable orbital and combine that with a tiny rigid orbital, does that make a good combination? It turns out no. What we want is we want to take a big polarizable orbital and do an LCAO with another big polarizable orbital. Those big polarizable orbitals we call soft. The small orbitals we call hard. And so HSAB stands for hard, soft, and AB stands for acid-base. So hard, soft, acid-base theory. And so what makes a good combination is soft, soft, good combo. Hard, hard, good combo. Hard, soft, not such a great combo. And so what it turns out here is this. Lead is soft. If lead is soft, then we want another soft one. These heavy metals are typically soft. So what's softer, big iodide or small chloride? Softer. Softer meaning more polarizable, less dense electron cloud, that kind of stuff. Iodide. Iodide turns out to be softer. So this is actually a favorable combination. If we were looking at this LCAO, HSAB, then I would have predicted iodide would be better than chloride because iodide's soft. And so this would be soft, soft, whereas chloride's much harder. Does that make sense? And so it's not that we were wrong. If we assumed 100%, then we would have been correct. And if it were 100%, we would have been correct. But there's got to be a significant covalent bonding interaction here. Not only that, there are other factors that play into this. So our prediction turned out to be incorrect here because we weren't starting off with the correct basic assumption here. And so in terms of HSAB, this is a better combination here than this. So we'll talk more about HSAB later, LCAO and MO theory a bit later. But MO theory, if you've forgotten some of the MO theory, it wouldn't hurt to go back and look, at that chapter 10 or whatever chapter that was. All right, this is the case. This turns out to be less soluble. This turns out to be more soluble. So which one is favored? PBI2 is favored. So the downhill direction is the reverse. The driving force is reverse. So the acid is a tie. The solids predict the driving force in the backwards. So the downhill direction, this is uphill, going left to right. The downhill direction is right to left. The driving force would be backwards. And there's no gas. So if there's no gas formed, the acids are tie, and the precipitate or the driving force here for the solid-to-solid transformation is backwards, then there's no driving force. If there's no driving force, then we predict that there is no reaction. No reaction we label NR. So what do you do? If you're on a test, you can make the assumption. I'm going to assume it's the ionic bonds, and then for ionic bonds, we can do it this way. Based on those arguments, then this should be reasonable. Or we could look up the numbers. If we actually look up the data, then we see it's got to be the reverse. All right, you could try working some of these others, aqueous ammonia and this iron 3 sulfide and acetic acid, maybe as homework. What we're going to do today is we're going to move on to part 2. So let's take a look at that. Here. Okay. These are just 3 different definitions. Arrhenius, Bronsted, Lowry, Lewis. We only need one definition. Which definition is that? Bronsted is not enough. Actually, which one is the most general definition of an acid and a base? Lewis. Arrhenius is the least. So Arrhenius is pretty worthless. We don't spend much time looking at Arrhenius because it's the narrowest definition. Arrhenius acid is just H plus. Arrhenius base is just OH minus. Bronze has a broader definition, so it's more useful. An acid is a proton donor. A base is a proton acceptor. But all we really need is the Lewis. The problem with Lewis is it's a lot harder to analyze things in terms of Lewis acidity and Lewis basicity. As an acid is an electron pair acceptor. A base is electron pair donor. When an electron pair is accepted and an electron pair is donated, we make what's called a coordinate covalent bond, which we'll talk about later. Arrhenius acid-base reactions, there's only one, H plus OH minus. What does this make? Makes water. H plus is a strong acid. Water is a weak acid. Hydroxide, this is a strong base. Water is a weak base. So we have driving force for this. Taking a strong acid and strong base and reacting them to form weak. In this case, water is both the acid and the base on the product side. This we call acid-base neutralization reaction. Okay, let's move on here. So, Bronsted is going to be a lot more useful, but it only gets part of the acid-base universe. It doesn't get the whole complete acid-base universe. In order to get the complete acid-base universe of acid-base reactions, we need to use Lewis. But Lewis is a lot more complicated. Bronsted is a lot easier. And so we're going to look at part of the acid-base universe, the ones that we can determine using Bronsted-Lowry reactions. And the way I do Bronsted-Lowry reaction is, one, I inventory. Inventory just means look for all the acids and bases present. There could be more than one. If there's more than one acid or base present, then I look for the strongest of the acids and the strongest of the bases. Those are the species that are most likely to react, the strongest. And then 3, we transfer a single proton from the acid to the base. 4, we determine if there's a driving force, dF. If there's a driving force, then that reaction should be downhill and it should occur. If there's no driving force, it's uphill, and we predict no reaction or no significant reaction. Since we're doing this one at a time, a single H+, we repeat the steps in case there's further reaction that can take place. So we do it one step at a time. Okay, let's look at an example here. Phosphoric acid and sodium hydroxide. This one we could do either metathesis or Bronsted acid base. So what I'm going to do is first I'm going to do this as a metathesis reaction. If I do this as metathesis, it just follows the double replacement format. Phosphoric acid, H3PO4, and sodium hydroxide, NaOH. Here. It's an AB plus CD. So I need to take H plus and OH minus. H plus and OH minus makes what? Hydrogen hydroxide. Hydrogen hydroxide is or what are my products? Can you just see this and tell me what my products are? Double replacement. Did I miss anyone from Louisville? Name? One? Did I get you? Okay, name? Andrew? Andrew Herrera. Okay, anyone else? No. Somebody have the products? Water and H2PO4. All right, when we do metathesis, this is what I'd like you to do. I'd like you to react to completion. If it's not specified, now this conflicts with what I said earlier. When I was talking about H2SO4, I said to remove one hydrogen at a time. So if we had 2 hydrogens, I told you just to remove one. And therefore we formed H plus and HSO4 minus. However, when we do metathesis, we're going to remove all of them. If I remove all the protons off phosphate, then I'm just left with phosphate. And so the other product here is going to be sodium phosphate, Na3. That is, all the hydrogens are gone. Phosphoric acid we call a triprotic acid, and in reality the protons break off one at a time, but when we do metathesis we'll just go to completion. Otherwise, if we do these partial reactions, it becomes a headache. We're going to do partial reactions. We're going to do partial reactions in Bronsted because we do Bronsted one step at a time. Okay, so for this metathesis, we're going to do it all together like this. Water is a liquid. Sodium hydroxide is a sodium salt. It's soluble. Phosphoric acid is group 1, so that's soluble. What about sodium phosphate? Does that precipitate? No, sodium salts are all soluble. So there's no precipitate. So what else do we look for in terms of driving force? Yeah. So we're going from an acid here, phosphoric acid. And what's the acid over here? It's going to be water. So what's the stronger acid, phosphoric acid or water? Phosphoric acid. So we're going from stronger acid to weaker acid. And all we need is one. And so this will be our driving force. Okay, the third driving force is gas formation. But is water a gas or sodium phosphate a gas? No. And so we do have one driving force, and therefore the downhill direction should be forward. And the reaction should proceed. Since the reaction proceeds, I need to balance it. How many sodium hydroxides do I need to neutralize the phosphoric acid? 3. Because I'm neutralizing all 3 acidic hydrogens. How many waters will I form? Also 3. Okay, now it's balanced. All right, so we have this. This is the CE, the complete equation. Let's go to the ionic equation. The ionic equation, we ionize the strong acids, strong bases, and soluble salts. Is phosphoric acid a strong acid? Is it one of the 7 common strong acids? No, it's not. In fact, let's take a look at it really quick. Here. Let's name the strong acids here. The strongest of the strong acids is on this chart, perchloric. Did we already do this? HI is called
Iodic acid.
Close. Hydroiodic acid is that what HBr is
Bromic acid.
hydrobromic acid. HCl is hydrochloric. H2SO4 sulfuric. HClO3 HClO3 is chloric acid. HClO4 is perchloric acid. So we have chloric acid and perchloric acid is strong. HNO3 is nitric acid. H3O plus, hydronium. Can anybody name this acid? This one might be tricky. This one's called trichloroacetic acid. Trichloroacetic acid. It's borderline strong. HSO4 minus? Hydrogen sulfate ion, or another name for HSO4 minus? Bisulfate. H3PO4, we were just talking about that. That's called phosphoric acid. This one is a weird looking one. You probably don't know how to name this, do you? This one is called hexa-aqua iron 2 ion. Hexa-aqua iron 2 is an example of a complex ion, complex cation. All it is iron 3. Sorry. All it is iron 3 ions dissolved in water, and it's surprisingly acidic. It forms these complexes with water. So the waters attach onto the iron. And the acid is weaker than phosphoric, but stronger than, what's this acid called? HNO2. Nitrous acid. Nitrous acid is stronger than hydrofluoric acid. And then, do you recognize this? This is called a carboxylic acid. When you see COOH, and it's a one carbon carboxylic acid. Do you know what prefix we use for one carbon chains? Have you heard of this? Meth, eth, prop, bute, pent. So it's one carbon carboxylic acid. We call it methanoic acid. Methanoic acid has another name. It's called formic acid. A two-carbon carboxylic acid like this is called ethanoic acid. Ethanoic acid has another name. Do you know what it is? Ethanoic acid is called acetic acid. So this is acetic acid. And then we have carbonic acid. Do you see carbonic acid has quotation marks? That's because it's very unstable and decomposes into CO2 and H2O. And so carbonic acid is CO2 and H2O. There are two names for this H2S. One name is hydrogen sulfide. It's the rotten egg smelling gas. How would you name H2S as an acid, though? As an acid, we don't call it hydrogen sulfide. We call it blank acid. Hydrosulfuric acid. That's correct. That's good. H2S is hydrosulfuric acid versus H2SO4, which is sulfuric acid. And so a useful exercise is just to go down these. Next is dihydrogen phosphate, ammonium, hydrocyanic acid, or hydrogen cyanide, bicarbonate, monohydrogen phosphate, water. This is hydrogen sulfide ion, ammonia, hydroxide. This is weird. Hydroxide as an acid. Hydroxide is a weird one because it's what we call amphoteric. In fact, both of these are weird because ammonia is a weak base, hydroxide is a strong base. Why are these on the acid side? It's because they're amphoteric. So for example, if ammonia loses a hydrogen, do you know what it forms? If ammonia loses a hydrogen, it forms NH2. And it's not just losing a hydrogen, it's losing an H+, so the charge is NH2 minus. Do you know what we call NH2 minus? NH2 minus is called amide or amide, either way. And that's a very powerful base. And so for each acid we have over here on the left, we have something called the conjugate base on the right. And these are pairs. So if the acid is very weak, its conjugate base is very strong. Or if the acid is strong, its conjugate base is very weak. And so these are all very strong conjugate bases of these very weak acids. Methane we don't even consider. We don't even consider that an acid. What time do we go till? 3:55. I went overtime. All right. All right. Sorry. We'll wrap things up here. So we're gonna continue. We're gonna finish off the second part and the third part tomorrow, and then we're gonna start looking at nomenclature of complexes. So work on those metathesis reactions as homework tonight. Okay. Tomorrow. Tomorrow. I mean, just bring them in tomorrow. Yeah, the ones that are on the PowerPoint. You could try these Bronsted ones. We'll look at it. You can finish this, but the one we're working on now as well.
All right.